So, this is something you've seen before, that's inductively defined. How is 0 factorial defined? One's definition. 1 factorial is equal to 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2. Cascade like this. And inductively, way you get the next factorial is you multiply by the next number. So let's go over some inductive proofs. I want to kind of redo the one that I did last time. When you add the first n odd numbers, you get the number of things you added up squared. Proof. Okay, what's the base case? What's the smallest n? This makes sense. Let's see if this formula holds when this one. The left-hand side. 1 plus 3 plus all the way up to 2n minus 1. Now this is where this tells you where to stop. And if it is 1, where do you stop? 2 minus 1 is 1, so you stop it. So there isn't any of this other purple stuff, it's just 1. And the right side, so the formula works. For base case. Right, okay. Now this is called the inductive hypothesis. What we want to do now is we want to show that we've got a stairway to heaven. We've got to show that if we've ever got a rung on the ladder, then we've got the next rung. Right? So suppose for some m greater than or equal to 1, we have 1 plus 3, 5, 2m minus 1 is equal to. So we suppose that for some m greater than or equal to 1, we have this formula. We've already shown that we do have it for m equals 1. How do we, what we want to do is show that when we have it for m equal for this m, then we have it for the next m. What's the next odd after 2m minus 1? 2m plus 1. Everybody agree with that? Just kick it up by 2. I'm going to write it more explicitly than you said because just to kind of illustrate. It's actually replace m by m plus 1. It's 2m plus 1 minus 1. And if you multiply this out, this is exactly what he said. It's 2m plus 1. Everybody okay with that? Now, this is algebra, folks. So if I'm going to add that orange thing to the left side, I better do it over here. Great. So what do we have now? We have 1 plus 3, 5 plus 2m minus 1 plus 2m m plus one minus one is equal to m squared plus two m plus one. Everybody agree that's what you get from me? And what's another way I can write this? Plus one squared. Good. Notice that my formula works when I replace m by m plus one. So I've built the ladder. It works here, works there. So by induction, we've built the ladder. We know the bottom run, n equals one works. We know if it ever works, it works for the next one. So you've got that stairway to heaven. Do you all see the connection now? When I first wrote induction, it was a kind of the strange thing about, okay, suppose you have a subset of the natural numbers that contains one, and if it contains any natural number, it contains the next one, then it's everything, right? That's what you're doing. You're building the file. Okay, any questions on it? Yes.
So it really doesn't matter like the beginning of the formula, just like the two n minus one.
Well, so what we've shown is if this formula holds, then it holds when m is replaced by m plus one, and that's why the ladder works, right? Right, so let's look at some other examples. And I'm gonna do some mixed induction and show you how things tie together. Anybody know what this one is? You might have seen this in calculus, actually, when you saw looked at areas of the curves. No, that's only a finite number for sure. I've seen this one. I want to prove this both inductively and non-inductively. And for the first one, you might think it's superior because it actually shows what you want. I want to know what the sum of the first n integers is. I don't know at this point, so I'll call it S. Now, what's this? Nothing up my sleeve. That is also equal to S. Everybody agree with that? It's just, I've just rearranged it. I've written them backwards order. These is columns. What's one plus n? What's two plus n minus one? What's three plus n minus two? I hope you all see a pattern here. That's two S. How many n plus ones are there here? There's n of them, right? One, two, three. There's n of these n plus one. And so there's a proof that the sum of the first n integers is n times n. This is the best way to do this because we don't need induction here. And not only that, I basically did it from scratch, but I'm also going to now prove that this works by induction. That Shows. Okay. Let's compare them, shall we? So. K equals 1 to 1, K is equal to 1. So the left-hand side of that equation is 5, because you're only adding 1. Right? And if I put in 1 in this formula, the formula works. Now, we want to build a ladder. We've got the bottom rung here. We know that it works in the smallest case. We now want to show that if it ever works for any rung on the ladder, it works for the next rung. So let's see how that works. Um, right. So inductive hypothesis. Let's suppose for some m greater than or equal to 1, we have 1 plus 2 plus 3. I'll write it out so you sigma notation. Now, suppose it works for some value then. You gotta show it works for the next value. Right? So. Okay, so let's see what happens for us here. Let's look at 1 plus 2 plus 3 plus m minus 1 plus m. So I'm going to start from my inductive hypothesis. This holds right here. And then I'm going to add the next term. What's the next term here? And so I better add it here. So this gives me okay, I want to write this as a single fraction. Just a fancy way to write n plus 1 here. Gosh, it looks like I made a mess, but do you see something that I can do here? There's a factor of n plus 1 here, isn't there? So this is actually three. So what I have is 1 plus 2 plus m plus is equal to. I'm going to write this out grammatically. Notice the formula holds again, right? Because what my formula says here, the inductive hypothesis, is to add it up to m you just take whatever this is plus the next integer divided by two. And that's exactly what happens here. You go up to n plus one, this plus the next integer divided by two. So by induction, this formula always works, right? Because if it works for the rung m, it works for the rung n plus one, and we've shown that the bottom rung holds. Okay, any questions? Um. How about this one? Actually, before I do this, let me illustrate something about kind of math checking these out. So. You know, remember what this one was? We had it first in odd terms, or odd numbers. What should this be? What's it? Okay, how did you get that? That's a good way to get this. Where did you get this? Well. You see common factor here? We figured out what this one is. This is two times n plus one over two, which is n plus one. Do you see another one that's in this? So there are many ways to kind of see that this works. I'm sorry. No, I think this is square. What do you mean?
Oh, so we, another way to write that.
Well, so yes, you can add one to every term here. So notice this kicks us up to a 2, 4, 6, all the way up to 2n. How many ones did I put in here? N of them. And one last look here. Now that we know this, what happens if I add these two equations? All right, I get 1 plus 2 plus 3 plus 4. And where do I quit? If I add the left sides of these equations. 1, 2, to it. Everybody agree with that? The other side of the equation should be 2n squared plus n. Right? Does this come full circle for us? Well, remember. That should be 2n comes the next integer divided by 2. That's the formula we just proved by induction. And this turns out to be n times 2n plus 1, which is 2n squared. So there's a couple ways that we tie all this stuff together and it comes full circle. Okay, any questions? Here's another. So I would recommend in practicing this, obviously, as you might expect, on Friday, I'm going to give you more problems, and there's going to be a lot of induction on it. You can find induction problems all over the place. Practice these a lot. Once you get slick with it, it's not too bad. So I'm going to do this example. I think law. There's some of you that are engineers and physicists and whatnot in here. N factorial and 2 to the n. What happens to these numbers as n gets very large? They certainly both go to infinity, right? And they do it very quickly, right? How many of you are aware that n factorial gets very large very quick, right? 2 to the n gets very large very quick as well, right? That's the old, do you want a penny doubled every day for a month or do you want $1 million, right? Which one of them is bigger?
The factorial gets bigger faster, that's good.
N factorial. But wait a minute, this isn't always true, is it? What's 1 factorial? And what's 2 to the 1? That doesn't work. What about 2 factorial? And what's 2 to the 2? 3 factorial. 2 cubed? What's 4 factorial? 24. What's 2 to the 4? I think factorial kicks up things, but not until 4. So my claim is, this is something that's important if you want to gauge sizes of stuff in things like engineering and physics. N factorial gets large, much bigger than 2 to the n, and is in fact strictly bigger than 2 to the n. This doesn't really start happening until n equals 4. Then it gets rather dramatic. But anyway, let's just show that n factorial is always bigger than the n for n equals 4. So what we're trying to do is we're trying to prove this statement about infinitely many things, 4, 5, 6, 7, forever and ever. Sounds like induction to me, right? Because I need something to help me do infinitely many things, right? Okay. In induction, there's 2 things. There's find the bottom rung and then build a ladder. Place case here.
N equals 4.
N equals 4. This is the first relevant case. That's an important thing. Notice I'm gonna basically steal what you guys told me here. There's my bottom rung. Everybody okay with that? Now, we've got to build a ladder. So inductive hypothesis here. Suppose for some m greater than or equal to 4, we have m factorial is strictly bigger than 2 to the m. Now, let me kind of report all of this. Yeah, next week. View session. Here's our goal. This might be part of your scratch work if you're writing this up formally. Probably shouldn't be part of your first, right? I'm writing this down here, so I think about where I want to go. Where am I heading? I need to show. Plus 1 factorial is bigger than 2 plus. So this is my tool. And I need to somehow come up with this. Any ideas on how I'm going to use this and leverage it to act?
N plus 1 factorial is n factorial times n plus 1, whereas 2 to the n plus 1 is 2 to the n plus 2. And we already know that that's something.
Fantastic. That's a great observation. His observation is this. This thing is m plus 1 times n factorial. Right? And this is just an extra 2 times this, right? If this is already bigger than this, basically I'm hitting this side with m plus 1, which is, gosh, that's going to be at least 5. And I'm only hitting this side with a 2. Right? So it's got to continue to be bigger. Everybody agree with that? Let me see if I can put down something that's more mathematically concrete. So here's my inductive hypothesis. Since m is bigger than or equal to 4, and m plus 1 is bigger than or equal to 5, which is strictly bigger than 2. All right. Everybody agree? Where did that 2 come from? Am I having a stroke up here? No, I'm looking ahead because this 2's going to come up. Hopefully we can see what happens. So these are both positive numbers, everybody agree? And so is n plus 1. So I can multiply everybody agree with that? I just took that and multiplied both sides by n plus 1. Doesn't change the inequality because n plus 1 is positive. Agree? And what's n plus 1 bigger than? 2. It's bigger than 2. So this is bigger than 2 times 2 to the m. So let's collapse what I've got. This is m plus 1 factorial is greater than 2 the n plus 1. So I've built the ladder. I've shown this. So it works at 4, and this shows if it works for any integer, it works for the next one. So n factorial is greater than with 2 n for all n greater than or equal. And there we can definitely show. Okay, any questions on that?
So how would you go about proving that? Because right now you just have integer steps, so you would have to go further to prove any n that's not an integer. Like right now?
The factorial is not defined for anything inside the integer anyway.
Yeah.
Right, of course, you can generalize it to the gamma function, but, induction is defined for discrete integer, right? So, to prove something like. mm, So he points out, so he was asking, correct me if I'm wrong, he was asking, okay, how do you generalize this to, this thing only takes care of positive integers, right? What if you want something else? Like, what if you want to prove something like x is bigger than log x? Or all x greater than 1? Induction's not going to work for this if x is taken to be any real number, right? Because you need the properties of the natural numbers, which is not true of the integer. There are other ways to do this. You can do things with derivatives. You can do induction to show that x is bigger than log x for every integer bigger than 1, for sure. But you'll have to come up with something different to plug in the gaps, right? Okay, other questions? Yes.
Do you have to show like that it's not true or like n is less than?
No. Yeah, that's another good question. No. Don't do anything I don't ask you to do. All I ask you to do is show in this case, this holds, right? So, and actually, of course, this equation, you need m to be greater than or equal to 0 just to make sense in the first place, right? Because factorial is only defined for 0, 1, 2. And we all already went through 0, 1, 2, and 3 and showed that this doesn't work. It's not a thing. Okay, here's another one. Consider I only put 3 terms in there, but I hope you will see the pattern I'm trying to convey. I'm gonna write something for you now for just a moment. Consider the following sequence. So this, actually, if you had a decent Calc 2 class, you might have seen a problem like this. Consider the sequence, square root of 10, then square root of 10 plus radical 10, then the square root of 10 plus square root of 10 plus radical 10. So the problem you might have seen in Calc 2 would be, does this sequence converge or diverge? So just for fun, we'll go back and Calc 2 for a bit. Anybody got a guess on this? Converge, diverge? Yeah, but the ratio test is really for series, isn't it? Sequences.
With diverge. And with diverge.
This one actually converted. I know what you think. It seems to be getting bigger, right? And maybe it just goes up forever.
Oh, I see. It's square root of 10 plus. Square root. It's trying to box something.
Yeah, that's right. It's the square root of the whole shebang. It's not clear this converges, though, does it?
No.
But it does. Anybody know what it converges to? This actually converges to 1 plus the square root of 41 over 2. That's even less obvious, isn't it? But it does converge. Does anybody remember? So what did you do when you were in Calc 2 and did sequences in series, right? When you did sequences in particular, there were a couple of things you did if you got a sequence. The first thing you did is you treated it like it was a function, right? Like if I asked you, oh, what happens to 1 over the square root of n, right? What happens to that sequence? You just like, oh, look, 1 over square root of x goes to 0 as x goes to infinity, right? That's one thing. You can't really do this here, right? I don't know a function that does that. Right? Another thing is, she did something like a squeeze theorem or something like that, that doesn't really seem appropriate here, but there was actually a big theorem that you probably had in calculus. Does anybody remember what special type of sequence converges? Anybody remember a bounded monotonic sequence? Anybody, can anybody tell me what a bounded sequence is?
So this sequence that has, it's between two numbers, like there's an.
Okay. So think of a sequence as a set of dots. You plug in one for something, it's a set of dots. Like this. A bounded sequence has a ceiling and a floor. So the terms in the sequence are always, they're always under the ceiling and over the floor, right? And anybody remember what monotonic is?
They're always. They're always.
Monotonic, mono from the Greek. Meaning one, do one thing, and tonic meaning. Tonic, whatever that means. But anyway, a monotonic sequence is one that either, it does one thing, it's either always going up or always going down. So there's a theorem in calculus that says if you have a bounded monotonic sequence, it must converge. And notice this one's monotonic going up, right? It converges to the lowest roof you can make, right? If it were going down, always down, and it's got a floor, it converges to the highest floor. Right? Actually, to prove this, it's really a lot more subtle. I wave my hands. This is not a proof. This is just me giving you an intuitive picture. But here's where the induction is going to come in. Show this sequence is bounded and monotonic. And we're going to need induction. Well, before I can do induction, I need some kind of something that I can work with, a formula. Here is how the sequence is defined. Can somebody describe, given my pattern here, if I have a term, how do I get the next term from it?
For 10 plus that.
Okay, he's right. How do I get the next term after this? Well, I take this term and add 10 to it. And then I take the square root of the whole shebang. Everybody agree with that? This is one of the hardest parts of the problem right here is making this observation. Notice we do the same thing here. How do we get the next term here? Take 10 and add it to this term and then take the square root of the whole thing. Everybody agree with that? This is what is going to allow us to do induction. So I've got two proofs to do here. I've got bounded and I've got monotonic. So I claim each term AN of sequence satisfies can anybody give me a floor? I don't care how naive you are. What's every term of that sequence better than a regular? Okay. Be more naive than that. What you say is true, but it depends on how do you know the next term is bigger, right? Well, it is because it's square root of 10 plus a little bit more, but how do you know that those other terms, how do you know that? Zero. Okay, I like that one, right? It's a truly lazy answer, and lazy answers are very good, right? If you can get away with it, right? Everybody agree that everything in that sequence never negative, so it's at least equal. Okay, this one's a little slicker, right? So maybe back to you again. What about a ceiling? Again, you can be naive if you like. A billion. He was correct, and that will work when we do the proof. I just don't want to write 9 zeros all the time. So I will do this. We try that. Maybe, I hope. But the proof will show me whether this is. I claim this. Each AN is greater than or equal to 0 because it's the square root of a positive number. So that's not the interesting part of it. We show AN is less than or equal to 10 by induction. And I'm gonna write my important equation for here. That is to say, AM plus 1 is square root of 10 plus. Okay, base case. What is the first term in this sequence? Square root of 10, and I don't know much, but I do know that that's less than or equal to 10, so chicken window. Everybody agree? Okay, now, my inductive hypothesis. Oh. M greater than or equal to 1, and A M plus 1, I'm sorry, AM is less than. I want to show the next term is less than or equal to 10. Okay, so this is my inductive hypothesis. I'm assuming that the nth ladder on the run holds. I want to show that the next run on the ladder holds, right? How am I gonna engineer this? Right? How am I gonna kick this down the path?
You define AM plus 1 in terms of AM, and then you square that while testing to see if it's less than or equal to 10.
Okay. How do I get from a term to the next term? I add 10 to it, right? Right. So what I have so far is 10 plus AM is less than or equal to 20. And how do I complete this? How do I get from here to AM plus 1?
You take the square root of the
Take the square root. And so this gives by the way, how do I know that? So what did I do? I took the square root of this is less, so this is less than or equal to this. And then I say the square root of that is less than or equal to this. Why is that? How do I know I can do that? Actually, you can use calculus, as a matter of fact. What do you know about the square root function? Does it look something like that? Is that function increasing, decreasing, or neither? It's increasing. So that means when you have something smaller, so if your x coordinate is smaller, then the corresponding y coordinate has to be smaller. So there I've used a little calculus to justify this. Everybody okay? And I don't know much about the square root of 20, but I do know it's less than or equal to 10, because this is in fact the square root of 100. So what have I come up with? Check. Notice this is significantly smaller than 10, right? And so I've got, and if I'd gone with your billion, I mean, it would have been even more dramatic, right? Okay. Any questions on that? So AN is less than or equal to 10 on all N by induction. Okay. We can at least get started on the second induction. Sequence AN is by the way, monotonic here means always increasing or always decreasing. Which do you think this one is? It's always increasing because otherwise I'm dead wrong. Radical 10, and this is radical 10 plus a smidge. So this is getting bigger. It gets a little bit less clear, right? Because you're taking square roots of stuff, right? That this is always increasing, but it is. We're going to prove this is monotonic. And by monotonic in this case, we're going to show that it's increasing. So, base case. So let me write this more carefully. Show for all n greater than or equal to 1. What do we want to show?
A in 20 squared A.
Show that the next term is greater than or equal to the induced. Okay, base case. Base case works because radical, this is actually a little bit more than radical 13, bigger than radical 10. Everybody agree with that? The inductive hypothesis, I think this was easier. Suppose for some m greater than or equal to 1, we have am is less than or equal to am plus 1, and we need to show am plus 1 less than or equal to am plus 2. We need to show this is true for the next sequence, right? So if this one is less than this one, we need to show that this one is less than the next one. Everybody okay with that? So this should be easy to finish off. What do? I want to do just like I did before. I want to ratchet this up to the next term. So add 10 to both sides. And since this one is smaller than this one, the square roots preserve the order. And what's another name for this? A m plus one is less than or equal to a m plus two. So sequence is increasing by induction. Because we numerically verified the base case, and we showed if you have a run on the ladder, you get the next one. Any questions on it? Okay, look over these, try to practice some easy induction problems, some warm-ups, if you will, and let me know if you've got any questions.